Okay, in this video we're going to look at an introduction to the Rankine cycle. We'll do one simple example, but this is the basic model that's used in most steam power plants. And basically, the simplest model of this starts with a pump. So you're going to take a liquid at P1 and pump it up to a higher exit pressure. And we're going to assume that it's Q equal to 0 during this stage. And it's going to come out at a high pressure, but still liquid. We're then going to boil this. So we're going to have heat transfer in to increase the temperature to either the saturation temperature or something higher. Then we're going to run this hot steam, or whatever fluid it is, through a turbine, and that's going to perform work and decompress the material from P4 back to the original pressure P1. Again, we're going to assume that Q is 0 here, and then we will finally bring it back to the original state by condensing it back to a liquid at that original pressure. If you look at what this looks like on a diagram, first of all, if you're looking at a little flow diagram of the equipment, comes in at state 1, goes through a pump with work input, comes to state 2, goes through a vaporizer or a boiler with heat transfer into the equipment, leaves there at state 3, comes into an expander or a turbine, work is going to be produced, leave at state 4, and then go to a condenser. Heat is going to be taken out of the system, and we'll leave at state 1, the original. And if we were to draw this on, say, a TS diagram, it might look something like this. Okay. The equations, and these are what we've developed in the past few videos reviewing pumps and boilers and so forth, are these. I'm going to have no heat transfer in the pump or the turbine, no work in the boiler or condenser. For my pump, it's a liquid, so I can use V delta P as an approximation for work, but that's not going to work for the turbine. I need to definitely use enthalpy change. Best way to understand this is to look at an example. So here's a very simple one. I'm going to use warm water from the ground, so a nice renewable resource, as the energy source for a Rankine cycle using refrigerant 134A. It's going to be saturated, leaving the boiler, so saturated vapor. The temperature will be 85 degrees at the exit of the boiler, and the condenser operates at 40 degrees. And based on just that, let's find the specific work of the pump and the turbine, and the heat transfer in the boiler, and the thermal efficiency. So let's start looking at this. So I've reminded us of the drawings up here. The given information was the condenser operates at 40, and the boiler goes to 85 degrees as a saturated vapor. So this is all the information that I'm given, and what I want to do is figure out all the rest of the properties. Now for state 3, I have 2 pieces of information, so I can use that to get the rest of the data for state 3. But what about the others? Well, I'm going to need to use my assumptions. So, okay, the things that I know, well, first of all, at 85 and quality of 1, I can look up the rest of the data. And I did this using the data out of Simplified and Berniaki's book. And I ended up with these values. But I also know that I can assume my condenser is constant pressure and my boiler is constant pressure. My pump should be constant entropy, and my turbine should be constant entropy. So this doesn't give me a lot to work with, but I also can assume that this is a compressed liquid. Not sure how much that will help me. And it's very reasonable to assume, and this is strictly an assumed value, that coming out of the condenser and into the pump, it's a saturated liquid. This is a very reasonable assumption, but it is an assumption. So if we then take this information, and I can now have 2 pieces of information about the inlet to the pump, I can find this data using my assumptions about constant entropy and constant pressure. I can get these others. Now this state has enough to look up the data. And when I do that, I end up with this. But this one, I do not have a compressed liquid table for refrigerant 134A, so I'm stuck. So this is as far as I can go with the tables. But I've done really well for starting with only 2 temperatures and 1 quality. So now let's start analyzing the individual processes. So here's my data table as far as I was able to get it. I like to start with the pump just because you don't have to. Just start with anything and see how far you can get. On the pump, remember, I'm going to have to analyze this using the V delta P. So here I go. Here's my volume, my pressure change, and I got negative 1.7 kilojoules per kilogram. I can use this to get the enthalpy coming out of the pump because the energy balance still should hold. And so therefore H2 is H1 minus the work of the pump, or 258.1. A little bit higher than where it went into the pump. For the boiler, it's H3 minus H2, so I have H3, I now have H2, I can calculate that. And the turbine is H3 minus H4, and I can calculate that. If I wanted to do the condenser, it would be H4 minus H1. I want to look at the cycle efficiency. I really have all the information. The net work is the same as the net heat transfer. I would need to calculate the condenser heat transfer to add that in, or I can do it just from the work. They should be the same value. But 19 minus 1.66 to 2 sig figs, or to the, the 10th place is 17.3 kilojoules per kilogram. This divided by the heat transfer N, which happens at the boiler, gives me a 10% efficiency. Now in future lessons, we'll be looking at whether or not that's a reasonable value, how I can improve it, what other kinds of things could I do with the equipment to maybe make this a better system, and are there any operational issues I need to be aware of. So that concludes this lesson.